All right, looking at our last couple examples, our last problem here, number 20, it wants us to solve the following rational inequalities. Show your work using the x-axis number line with test points or by graphing it. Write a solution set in interval notation. So what we're going to do is we're going to do it using the x-axis number line. So we're going to use a number line to show our solution set. And we can talk about it graphically too. If you want to graph the rational, you can see your solutions from your graph, right, based off where it's greater than equal to, less than equal to, or greater than less than, depending on the inequality. But what we're doing here algebraically, we just want to use what we call the critical values, all right, to set up our possible solution set intervals. Our first step, in step 1, all right, we'll write that down here, is to find our critical values. All right, and the critical values are any undefined values and zeros to the related equation. So zeros are solutions to the related equation. So in other words, your x-intercept locations if you were to graph the rational. With that said, I'm going to go ahead and mention the first critical value. Undefined values. Let's go ahead and highlight the denominator here. We cannot divide by 0. We know x plus 5 cannot equal 0. So with that said, as we solve for x, we come up with a undefined value, right, of -5. X cannot equal -5. There's one of our undefined values. That's a critical value. So find the critical values. That's one of them. So I'm going to write those critical values down here as we find them. So -5 would be one of those. This is the undefined value. Now we also got to find the zeros. So let's go get those. So now let's find the zeros. And again, we're talking about, which I guess we should make conclusion, find the real zeros, right, where this graph would cross the x-axis. So that implies what? When does f of x, right, equal 0, right? So again, you can just take your function. All right, with that said, we got 4 minus x over x plus 5, and set it equal to 2. There's the related equation. So as we're solving that, we'll go ahead and clear out the fraction. So there's our related equation. So make that note. Related equation. Drop the inequality symbol, right, and put in the equal sign. Now as you're solving that, you're solving a rational equation. So our LCD is x plus 5. So we know we got to clear out the fraction. So we would multiply both sides by x plus 5. And as we do that, all right, what happens? All right, we no longer have any fractions to look at. So our first term, right, the x plus 5s divide out. So we're just left with 4 minus x equal to 2 times x plus 5. So a nice, simple, linear equation results. So we got 2x plus 10. And as we solve this for x, let's go ahead and get x by itself. So here's our resulting equation. So we have a linear equation result. So whatever equation results after you've cleared the fraction, whether it be linear, quadratic, we know in linear, we got to go find out what x equals. We got to isolate it. So I'm going to go ahead and get x by itself. So go ahead and subtract this 2x over here. Go ahead and move the 4 over. It's minus 4 on both sides. Right, as we do that, our equation now reads -3x equal to 6. Right, and that gives us a critical value. As we solve for x, we get -2. So x equal to -2. So here's the zero of related equation. So that's a critical value. So -5 and -2, right? Looking at our critical values on this one. So again, the zero, the related equation, forms a critical value. So we found them. We got one undefined value, right? We have 1, 0. Now we're going to use those to form our possibilities of solution set intervals. We're going to place those on here. So let's go ahead and place -5. So here's all real numbers x. Here's our x-axis number line. As we place -5 and a -2 on here, right? Remember, -5 is an undefined value. It was a 0 the denominator. If you were to graph it, this is the location of your vertical asymptote, right? So it would be a vertical asymptote at that location. And -2, right, is a 0. It's a x-intercept location. But with that said, we have the following possibilities. So let's set up our test intervals. So what will our test intervals be? So we have what? -∞, -5. And we need a parentheses on -5. Make sure we don't include that. That is a undefined value, right? So our denominator became 0. That's where our vertical asymptote is. We also have the values here greater than -5, right, and less than or equal to -2. A bracket on -2. And then we have the region from -2 to infinity. So all values greater than or equal to -2 to infinity. So we got to test these intervals and see which works and see if we have a solution. So there are our test intervals. We've set those up, and now we got to test them. So pick a test value. So something easy to work with. I'm going to pick, for example, -6. -6 would be an easy integer value to use. I'm going to pick -3 here as my test value. -4. All right, those are my two integers. Either one would be an easy one to plug in. So picking an easy value to work with. And then over here, I'm going to use 0 whenever I can. I know 0's in that interval. All right, so with that said, let's find out what works. So it's -6 in the solution set. So we can go test it. So as we plug it in, I got 4 minus x, 4 minus -6, divided by -6 plus 5. And the question is it greater than or equal to 2? So as we simplify, well, 4 minus -6 is 4 plus 6. It ends up being 10 in the numerator, divided by -1. And that's -10 greater than or equal to 2. Well, it's not true, right? -10 is less than or equal to negative, and that's 2. So it's not true, right? So again, it's not in the solution set. So we're looking at testing those values. We only need one number. So that implies all the values less than -5, all right, are not part of the solution set. So we need to exclude those x values. All right, now as you go to our next interval, we got to look at the values greater than -5, right, and less than or equal to -2. Let's test it. So we plug it in, go back to your original inequality, 4 minus x, 4 minus -3, divided by -3 plus 5, is it greater than or equal to 2? Well, 4 minus -3 is 7. -3 plus 5 is 2. I've got 7 halves, and 7 halves is what? 3.5 or 3.5. And 3.5 is greater than or equal to. So this is a true statement. So that implies solutions. So we got to include this set. So yeah, that implies -5, all x values greater than -5 and less than or equal to -2 in the solution set. All right, and then our last interval to test is -2 to infinity, and then we'll test it with 0. So let's go ahead and plug that in. So as we plug in 0, we get 4 minus x, 4 minus 0, divided by 0 plus 5. Is it greater than or equal to 2? Well, that's 4 over 5. That's 4/5. 4/5 is not greater than 2. 4/5 is less than 2. So it doesn't work, right? It's false. Not true. All right, so that implies not in solution set. Now, with that said, we've got one interval. All x values greater than -5, right, and less than or equal to -2. So looking at our solution set of this problem, that is it. So all x values greater than -5, less than or equal to -2. Right? So we solved it. And we did that by finding what? Our critical values. Once we find our critical values, which are our undefined values in zeros related equation, right, then we can go and set up the x-axis and set up our intervals to test. And let's do the same thing in our next one. So let's go ahead and look at first step, x minus 4. Well, we know x minus 4 cannot equal 0, so we're finding undefined values. X cannot equal 4. That's a critical value. And over here with our second denominator, x minus 1 cannot equal 0. So that implies x cannot equal 1. So there's two critical values. So down here as we're writing our critical values for our next example, we've already got two of them. We've got 1 and we have 4. All right, the undefined values. And we'll make note of that beneath it. All right. Now we need to find our zeros, the related equation. So now I got to solve the related equation next. Any solutions to the related equation, right? Those are critical values also. So that implies what? Let's go ahead and work this together. That implies -3 over x minus 4 is equal -6 over x minus 1. And as we're solving a rational, we got to clear out the fractions. So our LCD, we have x minus 4 times x minus 1. The product of our different factors is only 2. So as we multiply those together, x minus 4, x minus 1, let's go ahead and do that on both sides to every term. And what happens when we do that? We cancel out these common factors. So we get a new equation without any fractions, which we know is how we solve rationals. I got -3 times x minus 1 left on the left side equal to -6 times x minus 4 on the right. And we got a linear equation resulting. All right, so to solve that, we're just going to simplify the sides and then get x by itself. So let's go ahead and distribute. So -3 times x is -3x. -3 times -1 is 3. -6 times x, -6x. Plus 24. And as we're solving for x, let's get our x terms together. We'll go ahead and add this 6x over here to the other side. I'm going to go ahead and subtract the 3. I'll move it over. And as we do that, what do we have? What does our equation now read? So now we've got 3x equal to 21. So that implies x equals 7. So there's a 0, right? There's the 0 of the related equation. So that's a critical value. So we need to include that. So that's the 0 from the related equation. Now we've got 3 critical values this time. 2 undefineds and a solution to the related equation. Let's go ahead and place those on our x line. So I'm going to put them on here. I got 1, now we got 4, and then I've got 7. Now with that said, 1 and 4 are undefined locations. So graphically, maybe you're checking it with your grapher. These are where your vertical asymptotes are. These are breaks in your graph. So as you look at your x-axis, here's our test intervals. So we'll write out our possibilities for solution set. So we got all the values, what? Less than, what? 1, so -infinity to 1 with the parentheses. We have 1 to 4. We have 4 to 7. Now 7 we have to include with a bracket, right? That is one of our solutions. And then we have 7 to infinity. So there are our regions. There are our test intervals, right? We're looking at the possibilities that we have here. Now we got to pick a test value. Now is the easy part. We've set up the intervals using the critical values. Now we need to test it. Now, -infinity to 1, Yeah, I'm using 0. 0's in that interval. 1 to 4, I'm going to use 2. 4 to 7, I'm going to use 5. Easy one. 7 to infinity, I'm going to use 8 here. Those are my test values. Let's see if they work. So let's plug it in. So as we test it, so I got -3 divided by 0 minus 4. Question is it less than or equal to -6 divided by 0 minus 1? So as we simplify, we end up with -3 over -4, less than or equal to -6 over -1. And that's 3/4, right? Less than or equal to 6. Well, that's true. 3/4 is less than 6. So we have a true statement. So that implies solutions. So we must include, right, that interval. That's going to be in there. Now as we look at the next interval, 1 to 4, let's go test it. So we take out our x, let's plug in the test value. So out comes x, in comes our test value of 2. So -3 divided by 2 minus 4. Is it less than or equal to -6 over 2 minus 1? As we simplify, I get -3 over -2, less than or equal to -6 over 1. So I have 3/2, less than or equal to 6. All right, as we're simplifying that down. That's a -6, somebody check me. Now 3/2 is not less than -6, so it doesn't check. So again, this is false. 3/2 is greater than -6. So a false statement. So it implies we need to exclude that from the solution set. All right, and then we got 2 more to test. So let's go at our last 2 intervals. About 4 to 7. Let's test our last interval, or next to last. So looking at 5, we have -3 divided by 5 minus 4, less than or equal to -6 divided by 5 minus 1. And simplifying down, that's -3 over 1, less than or equal to -6 over 4. -3 less than or equal to, well, -6 over 4 is -3/2 reduced. Yeah, -3 is less than -3/2. That does check. So we have a true statement. So that is true. So that implies solutions. We need to include those. So right now we have 2 intervals. We have all x values less than 1, and now we have all the x values greater than 4, less than or equal to 7. Let's go to our last interval. We haven't tested the last one, so we'll go ahead and test it. How about 7 to infinity? Again, my test value, I'm testing with 8. So as I plug that in, that's going to be -3 divided by 8 minus 4, less than or equal to -6 divided by 8 minus 1. As we simplify that down, that's -3 over 4, less than or equal to -6/7. Well, -3/4. All right. Again, question, is it less than or equal to -6/7? Well, it's greater than. All right. We're looking at that. So -3/4 less than or equal to. So again, plugging in that test value, right? See if it works. We plug that in. And simplifying down, again, I picked 8 as my test value, all right, to plug it in. All right, and then I had to check it. So again, we're looking at these critical values. So do make sure you're checking those out. But in our solution set, so we look at these, all right, we're looking at 2 intervals in our solution. All right, we've got all x values less than 1, and all x greater than or equal to, or greater than 4, less than or equal to 7. So again, we'll go ahead and X that one out. That was false. No solutions. Not in solution set. So let's write our conclusion. So of the 4 intervals that we tested, only 2 make up the solution set. So we'll write that down here beneath it. So that's solving rational inequalities, right? Rational inequalities, we got to find those test values, and those test values, I shouldn't say test values, those critical values, and those critical values are the undefined values and your solutions to your related equations, which are going to be your zeros. All right, so again, if you're graphing it, your zeros, of course, your x-intercepts. These undefined values and these rationals, they're representing our vertical asymptote. All right, so again, that's something you'll see if you graphed it, and you'll see when you graph, it is less than or equal to 0 between the intervals of -infinity and 1 and 4 to 7. So that'd be a way to check it, right, is to graph it. 'Cause that's how we did our polynomial inequalities. It was quick and easy to sketch this graph. To me, with rationals, this is easy. Go ahead and find the critical values, set up your intervals, and test them. So pick a number. One number works, they all work. If one number doesn't work, none of them are going to work in that interval. So you just need one test value, right, and you make your conclusion. So I hope that helps you. That's rational inequalities.